Lesson 17 covers the methods of producing electricity. So when we say produce electricity, what is it that we're producing? We're actually producing a voltage, okay, creating a potential, the ability to push current. So when we talk about creating electricity, we're talking about creating EMF. Okay, so the second bullet there says sources of EMF are devices or processes that change other forms of energy into electrical energy. Okay, so I'm not going to pretend to be an expert on this particular subject because it gets into chemistry and quite a bit of science stuff that maybe isn't my strength, but we will cover material, and really it's just these notes that will be the test information. So we'll work our way through this. What we have here are a list of the 6 basic methods of producing electricity. So these are forms of energy that we can convert into electrical energy. So friction is the first one. Historically, this is where the understanding of electricity began. We talked about this right back at the beginning of the conversation. You take two unlike objects, you rub them together, you create friction. What you end up doing is transferring electrons from one body to the other, and you end up with two charged bodies, one positively charged, one negatively charged, and that is static electricity. So that's kind of where the whole historical lesson and understanding began, was using friction to create electricity. Magnetism is a huge conversation. Last lesson was about magnetism. That conversation is going to carry on, a recurring theme. We'll get into that here in the next few slides, but again, very briefly, there's lots more of that conversation going to happen down the road. Chemical action, chemical reactions create a movement of electricity, or sorry, a movement of electrons, which creates a charge, which is potential, and that is the best example there is a battery. And so our next lesson and last lesson is going to be about batteries. So lots more to come on that. And then the next three, I'm going to try to glaze over really quickly because this is where the science gets pretty deep. And I end up over my head, conversation about pressure and heat and light. So we'll cover the points quickly. But that's not really where our understanding is going to take us. So we'll just look at the points when we get there. So friction. When we have two dissimilar materials and they are rubbed together, one material transfers some of its electrons to the other. The scientific term for this is the piezoelectric effect. And so here we have two objects rubbed together. And I was thinking there it might tell us what they are. Fur and rubber rubbed together. So as an example, so this was the early methods of creating static electricity, and that one mentions ebony rod across some animal fur. So again, we need a couple of appropriate dissimilar materials, rub them together, create some friction, and we get a transfer of electrons, gives us a static charge. You may or may not have heard of the Graaff Generator. That's exactly what's happening here. So we have a couple of pulleys that are driving a belt, and the belt is rubbing against a brush, and the brush is attached to this globe. And we get a transfer of electricities. The globe loses its electrons. They are transferred onto the belt, which then we can see the negative charges on this wand, and we can create a lightning effect from the wand back onto the globe as these electrons return to the globe, move from the negatively charged wand onto the positively charged globe. And you've probably all seen this somewhere along the way, some science show you watched on TV or the Science Center in Toronto. You touch this globe and you become charged yourself. That becomes evident from your hair, because what's happening now is all of your hairs are positively charged, which means they are repelling. And since your hair is light, that repulsion allows your hair to pretty much just stand up. Okay, so this is all the result of some kind of friction creating a static electric charge. Magnetism. So here's where my knowledge is much stronger, but we're not going to talk very much about it because, like I say, lots more to come later. But this is by far the most common form of creating electricity. Okay, when you think of all the electrical power plants, it doesn't matter what the source is, whether it's a coal burning power plant, a gas burning power plant, a hydroelectric dam, wind turbines. Okay, all of those actually produce electricity through magnetism. Okay, so the energy has to come from some source in the first place. So we're burning coal, we're burning hydro, the wind is blowing, water's falling, so we're using the force of gravity. Okay, that's the original force, the original energy, but we do not transfer that energy directly to electricity. It's got to go through stages, and in fact, what we do is we have to create a magnetic field, and then it's motion, and this is the part of the magnetism that I didn't talk about. I said that I'm kind of lying to you, so I guess I have to fill in a bit of a blank here. We cannot turn magnetism into electricity without motion. Okay, that's the key added element. And so that motion is the mechanical energy that comes from whatever the original energy source was. Okay, so we start with the original energy source. We turn that into mechanical energy by turning a turbine, typically. Okay, and then it's that turbine that's going to get the relative motion, which is what we need between a couple of conductors in a magnetic field, and we'll fill in all these blanks later. But finally, that is what turns that magnetic energy into electrical energy. Okay, so there's a number of transfers of forms of energy. Okay, but ultimately, all of our hydro producing facilities, with the exception of solar farms, uses magnetism to ultimately create the electricity. Okay, so the most common method, magnetism and moving electrical charges are inseparable. I'm just going through the points here now. By moving a magnetic field across a conductor, an electric charge is produced. So there's the magnetic field, the conductor, and the motion, which makes it all work. Okay, we call this the magnetoelectric effect. This is exactly how generators and alternators work. Okay, as well as much larger scale generating plants. Okay, and the final bullet there just says that there's way more to come on this, because this is a continuing conversation. There are an awful lot of details around magnetism, which encompasses a great deal of the conversation in the advanced electricity next year. So that's it for the magnetism. Let's move on to chemical. We have a few slides here about chemical reactions being used to create electricity. Energy is contained in different bonds that exist between elements and molecules. And when molecules are broken and the elements recombine, energy is either absorbed or given off. So we're talking about any chemical reaction. There's going to be a net gain or loss of energy as a result. Natural for all things to move from a high energy state to a lower energy state. So typically your chemical reactions ultimately are going to be giving off energy, and that's the energy that we're going to transform into electrical energy. So we take the ions of a battery cell, they dissociate and recombine to form different molecules, and those new bonds have less energy, so there's a release of energy, and the excess energy is given off in the form of EMF. Okay, electrochemical effect. So this is exactly what batteries do for us. Okay, so chemistry is the combining and recombining of atoms into molecules due to the different charge potentials. Fuel cells are really just an example of a battery. There's a difference, which I believe is explained in the next slide. The principle of a fuel cell, first discovered by Christian Frederick Schonbein, if that's his name. That's not test material. First fuel cell created by William Grove. But what is a fuel cell? Well, here it is, and without getting too deep into the chemistry here, we start with hydrogen. So this is a hydrogen fuel cell, and it breaks down into a hydrogen ion releasing some electrons. Now what happens is we recombine with oxygen. Okay, so we have to feed oxygen into this, and this is cut off because of me, but this says that we end up with H2O. Okay, there's the H2O right there, which is the byproduct of a hydrogen fuel cell. Okay, that's its That's what it gives off, water. Okay, but in the process of all of these chemical reactions, it's releasing energy. Okay, and so it's that energy that we will acquire right here, and we have our two terminals, our positive and negative terminals, which is the power supply to our circuit. Okay, so fuel cells differ from batteries in that they're designed for continuous replenishment. Okay, so the limitation of a battery, as you well know, is that as the chemical reaction carries on, the life of the battery gets reduced. Now, there's two types of batteries, and the next lesson we'll get into this more, but we have single-use batteries and we have rechargeable batteries. So the rechargeable battery, the particular chemical reaction that's taking place, we can apply energy and we can drive that reaction in the opposite direction, recharge the battery and allow it to be useful again. Okay, as opposed to a single-use battery, which you cannot apply energy and push the chemical reaction in the opposite direction. And so once the chemical reaction is complete, the battery is dead, and that's the end of it. Okay. A fuel cell here, on the other hand, while it's still the same idea, it's a chemical reaction that's releasing energy, we can simply continue to feed hydrogen and oxygen into this, and the chemical reaction just continues to perpetuate. Okay, is that the right word? Carries on. All right, so a fuel cell, a battery, essentially the same thing. The difference is the ability to just keep feeding this fuel cell. So here's our battery. Next to static electricity, chemical batteries are one of the earliest methods used to generate electricity. Okay, batteries provide a method of storing an electrical charge in the form of a suspended chemical reaction. So it doesn't really charge, it doesn't really hold electricity. Okay, we haven't talked yet about capacitors, but that's what a capacitor does. A capacitor will hold a static electric charge. Okay, a battery is different. We say that it's storing that electrical energy, except that it's storing it in the form of its chemical components. And once you put that battery into a circuit and you require electrons to flow through the circuit, that's what drives the reaction, and the chemical reaction takes place and it releases the energy. Something you may or may not be aware of, batteries are actually fairly dangerous. Okay, in their earliest years when they were first being developed, it was very difficult to figure out how to contain that chemical reaction. Okay, it simply happened very quickly, and that was the end of it. Okay, even today, a lot of your rechargeable batteries, I'm pretty sure lithium ion is one of the most significant ones, they're actually really volatile. Okay, just sitting in the box, the chemical reaction that is supposed to be suspended just happens, and with nowhere for the electricity to go, because there's no circuit for the electrons to flow, that energy simply gets released, and it's released in the form of heat, and we end up, the battery will spontaneously combust. Okay, another thing, you can increase the shelf life of any battery by storing it in the freezer, because of course the chemical reaction feeds off of heat. So if you remove more heat, it's going to slow down any naturally occurring slow chemical reaction, and the life of the battery, the shelf life of the battery, can be extended by storing it at a cold temperature. Just some interesting facts. So let's pick up the pace a little bit here. My knowledge and understanding of these are kind of limited. Pressure, mechanical stress of a crystal causes displacement of electrons, very much like friction. Pressure accomplishes the same thing. Okay, electron deficiency in one side of the crystal and a surplus on the other. We call this a piezoelectric effect. Okay, and this isn't a practical method of producing electricity for mass production, but for particular specific applications, it has its usefulness. Recognize here that it says it's used for measuring the shifting of tectonic plates. So that's a really practical, but a very small application. Okay, at a very small level. The piezoelectric effect. There are materials which will generate an electrical charge when squeezed, twisted, or bent. Okay, some of these are quartz, ceramics, cane sugar, topaz. Okay, that list is not test material. just finishes the thought. Again, on a small scale, here are some examples of where we can use the piezoelectric effect. In your barbecue igniter, okay, you push the button and it creates pressure, which creates an electric charge, which gives you the spark, which lights your barbecue. Okay, this is how record player needles worked. And I use past tense because, well, I don't know, records are making a comeback. Do you guys have record players at home? Microphones, earphones, strain gauges, sensors, actuators, so on and so forth. So there's lots of uses of the piezoelectric effect, you know, on very specialized applications in small scale. But in terms of large scale electrical generation, no. Heat. So when a junction of two dissimilar metals is heated, one takes on a positive charge and the other takes on a negative charge. So just like we need dissimilar materials to rub together to create electricity through friction, through heat, it's a similar sort of thing. Temperature sensing devices use this all the time. So you've got two dissimilar metals that are connected together. Okay, as it gets hotter, one expands more than the other, and it creates a twisting in the material. And this is exactly how old style thermostats worked. Okay, not so much the new electronic devices. So temperature difference exists between two different metals, and we call this the Seebeck effect, extensively in applications involving temperature measurement. Thermocouples and thermopiles, if those are terms you guys are familiar with. Maybe that's something that you guys are going to have to work with in the plant, troubleshoot, probably just replace. But this is exactly how a thermocouple works, is you're coupling two dissimilar metals which will expand and react differently to changes in temperature. And finally, light. When light strikes the surface of some materials, it gives up energy to the electrons. The extra energy causes the electrons to leave their atom, resulting in current flow. We call this the photovoltaic effect, and this is exactly how solar panels work. So light is composed of small particles called photons. When photons strike semiconductor material, they impart energy on those materials, raising their energy state and allowing the valence electrons to easily move from one orbit to another within that particular element or semiconductor. Okay, so here is your solar panel, and so you have a potential difference from the glass lens on the top or the silicone in the middle. I honestly don't understand how solar panels work. There's a nice picture. We're not going to test you on this. The test material is, can you produce electricity from light? And the answer is yes. Okay. The interesting part of the conversation to finish it all off is this, that the list that we looked at the beginning, forms of energy that we can use to create electricity, is pretty much the same list when we say what can we use electricity to produce. Okay, so with the exception of friction, because we can't create friction with electricity, but with the exception of friction, electricity can be used to cause the same effects as the ones that produce it. So we can use electricity to create magnetism, and we do that in many of our electrical devices. We can use electricity to provide energy to a chemical reaction to drive it. Okay, we can use electricity to create pressure. We can use electricity to create heat, definitely. That's kind of our main thing. We talk about that an awful lot. And clearly we can use electricity to create light. Okay, so essentially with the same list, minus friction, there it is. Okay, so that concludes this lesson, guys. We have one more to go. Watch for that and get ready for next week's test.